Hello and welcome. My name is Dominik Schröder, and in this episode I will show you how to construct a private key encryption scheme that is secure in the presence of an eavesdropper based on any pseudorandom number generator. So stay tuned. So this is the following construction that we're focusing on in this episode. So we are interested in the construction of a private key encryption scheme based on any pseudorandom number generator. So how does this construction work? Well, it essentially mimics the properties of the one-time pad in the sense that we are masking the message with the output of a PRG. So more formally, the construction consists as always of three algorithms. The first one is the key generation algorithm, and the key generation algorithm simply chooses the seed for the PRG. The encryption algorithm now takes as input the seed and evaluates the PRG on the seed, and the output of the PRG is then XORed to the message. The decryption works the other way around, meaning that the decryption algorithm takes as input again the key and also the ciphertext C. And now what it does, it evaluates the PRG on this key and XORs the result to the ciphertext. And what we will get is the message XORed to the PRG, XORed to the PRG, and these two elements essentially cancel out, and therefore we got the plain text back. So now let's briefly remember of the properties of the PRG. Well, first of all, the output is expanding, which means the PRG takes as input a seed of a certain length, for example n bits, and outputs a string of length n plus l. And in contrast to the one-time pad, this has the advantage that the key might be smaller than the message. The second property is pseudorandomness, which essentially says that the output of the PRG is computationally indistinguishable from a uniformly random string. So this concludes the description of the construction. And now, of course, we're interested in why is this actually secure? So let's take a look. So the question is, how can we actually prove the security of such schemes? Well, in general, honestly, it's quite easy in this setting because whatever you can use is given in the theorem. So let's take a look at the theorem. So let's take a look on the things that we actually want to prove. Well, the way that we usually start is by precisely looking at the theorem that we are given. And as you can see here, the theorem essentially contains several important components. The first one is the property, is the underlying assumption that we're using. And this property essentially says that G is a secure pseudorandom number generator. And if this is the case, then the theorem claims that our encryption scheme that we just defined has indistinguishable encryptions in the presence of an eavesdropper. Well, the first thing to prove this theorem that you have to do is to usually take a look on what are the actual properties that I have. And essentially the first one that we have is essentially the PRG. So the interesting property for us with respect to the security proof is the one that a PRG outputs strings that are pseudorandom, meaning that the adversary cannot tell whether it receives a pseudorandom string or a uniformly random string. So this is the first property that we have from which we are starting. This is our underlying assumption. And the second property, what we claim, is that based on this we get a secure encryption scheme that is secure in the presence of an eavesdropper. So here you can see the corresponding security game. In a previous video I discussed this notion in depth, so here I will only review the main steps. So these games usually proceed from the top to the bottom, and they precisely define what is happening in each step. Intuitively, the adversary should not be able to distinguish the encryption of two messages, M0 and M1, even if the adversary has chosen these messages on its own. And this is defined as follows. In the first step, the adversary receives the security parameter as input and outputs two messages that have the same length. And now we want to create the challenge ciphertext here, CB, and what we need to compute the ciphertext is essentially the key for the encryption scheme and the bit B that tells us which message we're going to encrypt. Once we created this challenge ciphertext, then it is given to the adversary here. And now the adversary has to tell us whether the ciphertext contains the encryption M0 or M1. And if it succeeds, which is represented by this condition here, in this case the adversary essentially outputs the correct bit and wins the game. Now, what the theorem intuitively says is that if the PRG is secure, then our encryption scheme is secure as well. So how can we prove the security now? Well, the way that we do it is we derive a contradiction, meaning that we don't believe the theorem is true and we basically turn it around. More precisely, we start with the assumption that the encryption scheme that we just derived is insecure. And if it's insecure, then we are essentially given an adversary, and we will use this adversary to break the PRG. And this is why we derive the contradiction, right? Initially, we assume that the PRG is secure, and therefore such an algorithm cannot exist, regardless of what we're doing. So let's take a closer look on the task that we actually have to do. As I just said, we derive a contradiction by saying that the resulting encryption scheme is insecure. So what does it mean? Well, it in particular means that there exists an adversary against our encryption that wins the game. At this point, we don't know how this adversary actually works. By our initial assumption that the resulting construction is insecure, we're just giving this guy as a black box. So what is the guy actually doing? Well, the only thing that this adversary knows is the environment it lives in, which means he only knows exactly this security experiment, and this is where the algorithm needs to be executed. In other words, you're giving an algorithm that is able of computing two messages of the same length, and if you give him one of the messages chosen at random, the adversary can actually tell which message it was, more precisely with some probability that is non-negligibly bigger than 1/2. Again, at this point we don't care how it works, we are just giving this algorithm by construction. So what are we going to do now? Well, we wish to derive a contradiction. And the way that we derive a contradiction is now by turning this algorithm into one that breaks our PRG. So what was the property of the PRG again? Well, let's take a look. So the PRG essentially, if you remember, the definition said that a PRG is secure if whenever we give an algorithm D, sometimes it's called the distinguisher, a uniformly random string and it outputs 1, has basically the same probability as we give D the output of the PRG and it outputs 1. So you can really think about this formalization in the following way. The distinguisher D gets either one of the two cases, either the pseudorandom string or the random string, and its goal is to output some bit B that says, well, either it was a PRG or it was a random string. So this is just a pictorial description of the same formalization that we have just seen. And now our task is essentially to find a mapping between the inputs of D to simulate the game for A, such that whenever A wins the game, D can break the PRG. Right, so what we have to do is exactly this. Somehow we are given a challenge from the outside, and we is now the algorithm that we are constructing to break the PRG, and we want to use these inputs to feed it into the algorithm against the encryption scheme. And whenever this guy actually succeeds, then we must show how to break the PRG. So here, for the reminder, here are the properties that we are giving. The first one is the PRG, right? This is what we would like to break. And in particular, this means that our goal is to construct an algorithm D against the PRG. The way you usually start is by simply looking at the definition and then you know what you're given. And as we now said, the definition says either I give you a string that is chosen uniformly at random, or I give you a string that is chosen by the PRG. And this is the only input that we are receiving at this point. So we are getting some input, and let's simply call this input in. And for example, if b equals 0, this is how you may want to think about it. N is computed as g of k, and for some bit b1, it essentially means that n is computed as a uniformly random string of the corresponding length. So this is the only input that we are given. And another thing that we actually have is, because we assumed that the encryption scheme is insecure, we can actually execute this guy here. So let's do it. So you can really think about it as simply having some method if you think of programming. And this is now just giving an interface A that you can use in order to break the PRG. So how can you use this interface? Well, pretty simple. The only thing that you need to do is to look precisely on how is this interface defined. And this interface is defined by the game itself. Well, you can actually run A, and what A will do, A will output two messages. Right, so this is essentially the case as we just saw here, namely the first step. A will output two messages of the same length. And now A is essentially waiting to receive some challenge ciphertext. And the question is, where is this challenge ciphertext coming from? The only thing that we have is essentially this input in. And now the idea is essentially to use this input in order to create this challenge ciphertext. Well, how do we do it? Well, what we essentially do is the following. We will choose a random bit b, let's call this tilde, and this random bit b will tell us which of the two messages we are going to encrypt. cb tilde is computed as the input in XOR the message mb. And we are feeding this back to the adversary. So let's think about what we just did. So essentially from this case here, we know with probability 1/2 it is actually the computation of the PRG, and with probability 1/2 is a uniformly random string. Eventually the adversary now will return its own prediction b prime. And what we will do is we will return 1 if and only if our b tilde equals to b prime, and the 0 otherwise. So let's talk about the intuition, why we actually choose our reduction in this way. Well, as we just said, we have essentially two cases, right? So the one case is the one where in is computed as g of k. Well, in this case, we computed our challenge ciphertext cb tilde as in XOR mb, and this is nothing else as g of k XOR mb tilde. So if you look closely, what is happening is that in this case, we are essentially perfectly simulating the case of the PRG. Right, so here it's a perfect simulation of the case of the PRG, and this in particular means that the probability that our algorithm dPRG on input in outputs 1, well, this probability is exactly the probability that the adversary wins against the private key encryption scheme. Why is that? Well, because the inputs are exactly given as in the corresponding game, and therefore from A's point of view, this is exactly what it's expecting. And what we know is that the adversary wins this game with a probability 1/2 plus something non-negligible. Where is this coming from? Well, initially we assumed that the adversary, or that we are giving an adversary that wins this game with non-negligible probability. So now we have to take a look at the second case, case 2. And this is the case where IN is essentially just computed uniformly, or it's just a uniformly random string of the corresponding length. And this essentially means that CB tilde is just a uniformly random string XORed with the message MB. And again, we're asking the same question: what is in this case the chance that the adversary wins the game? And because here we essentially have a perfect one-time pad, the probability is exactly 1/2. So the probability that D in this case, where it just gets a random string, outputs 1, is exactly 1/2. And this brings us to the final analysis. So in the analysis of the security proof, what we need to do is we need to understand how well is our adversary actually working. How well is our reduction, and the adversary that we are building is the reduction against the underlying primitive, actually working. And what we will do is, first of all, we need to take a look at the running time of D. And it's kind of easy to see that D runs in polynomial time because A runs in polynomial time, and because of handling all this mapping here, and this simple comparison can be done in polynomial time. So this is important because sometimes the reductions in fact might not be efficient anymore, and then there's nothing to show. So D PRG is a poly time, and in particular probabilistic polynomial time algorithm. This is fine. And now what we have to show is we essentially have to show that the probability that D PRG on input G of K minus the probability D PRG on input the random string R, we essentially have to show that the difference between both probability is actually non-negligible. So what we will do now is we will simply insert the two probability computations that we just did. In the first case, we learned that the probability is exactly 1/2 plus something non-negligible. And in the second case, where we're given a random string, it's exactly 1/2. And this means from the first case, we're getting 1/2 plus something non-negligible minus 1/2. Right, so this corresponds to this case here, and this corresponds exactly to this case here. And the 1/2s essentially cancel out, and we are left with something non-negligible, and this is then a contradiction to the security of the PRG. We have just shown that if there exists an adversary that breaks the encryption scheme, the eavesdropper security of the encryption scheme, then we can construct an algorithm that breaks the security of the PRG. And because we assumed initially that the PRG is secure, such an algorithm cannot exist. And this concludes the proof.